Hello everyone, and welcome to my lecture on Henry's Law and the solubility of gases in liquids. In this lecture, you will review the basic principles of partial pressure and how it can be used to calculate the concentration of gas in solutions, understand the factors which affect a gas's ability to dissolve in a liquid, understand the Henry's Law equation and when and how to apply it, and explore various real-life applications of Henry's Law. You can see an example of one of these real-life applications to the right here, where these carbonated drinks all hold dissolved carbon dioxide, which makes them fizzy. This is an example we will revisit later in the lecture. We have learned earlier in this semester various methods to calculate the solubility of solids into liquids and/or aqueous solutions. But what makes gases so different? How is the dissolving of something like hot chocolate powder different from the dissolving of carbon dioxide into a carbonated drink? Well, there are two factors which contribute to these differences, and these are temperature and pressure. Similarly to the solubility of solids and liquids in the previous lectures, temperature plays a big role in determining the solubility of gases and liquids. However, the difference arises in how their solubilities are affected by these changes in temperature. In solids, solubility can increase or decrease depending on whether the reaction is endothermic or exothermic. For example, in the top right diagram you can see that potassium nitrate solubility increases with temperature, while sodium sulfate solubility decreases. This contrasts the solubility of gases, which almost always decrease with temperature. This occurs because the more kinetic energy the gas molecules inside a solution contain, the easier it is for them to break the intermolecular bonds holding them in solution. This rise in temperature leads the solution's concentration of gases to be lower. One factor which was never considered in solid-liquid solubility was pressure. While changes in pressure are negligible in solids and liquids, it may not surprise you that pressure has a great effect on the solubility of gases. As the pressure of a gas over a solution rises, the concentration of that gas in the solution would also increase. This is because as pressure increases in the environment over a solution, particles are essentially forced into the solution to alleviate that pressure. This is seen in the diagram below. The pressure gradient essentially establishes an equilibrium with the solution, where an equal number of particles are diffusing into and out of the solution. As we push down on the piston, the pressure over the solution increases, and a new equilibrium would be established where there would be a higher concentration of molecules in the solution. It is important to note, however, that multiple gases could be in equilibrium at the same time, and this is where partial pressure comes in. Recall that the total pressure of the gases is equal to the sum of the individual partial pressures of every gas combined. Because of this, each gas contributing to the pressure over the solution will have their own separate solubility value which can be calculated. This leads us into our discussion of Henry's Law, which states that the solubility of a gas into a liquid is directly proportional to the partial pressure of that gas over top of the liquid. The Henry's Law equation is shown above in this diagram. As mentioned before, you can see that the solubility of a gas in question is equal to some constant K times the partial pressure of the gas. Solubility of the gas is equal to the moles per liter of gas dissolved into the solution. So by calculating the solubility of the gas, we know exactly how much of the gas is dissolved into the solution. This is shown in the figure below. As we double the pressure above the solution, we also double the number of molecules dissolved in the solution. But what is K? K in this context is referred to as Henry's constant, measured in moles per liter atmosphere, and the value changes according to the properties of the solute and solvent involved in the reaction. Therefore, to calculate the solubility of a gas in a liquid using the Henry's Law equation, we first must know what the K value between the two components is. You may notice, however, that one important component in solubility is missing from this equation, and that, of course, is temperature. Temperature will have a massive effect on the concentration of the gas in a solution, and because of this, temperature must be held constant while measuring solubility using the Henry's Law equation. Now that we have covered the theory behind the Henry's Law equation, let's try putting it into practice. A bottle of soda typically boasts an atmospheric pressure of about 3 atmospheres of carbon dioxide. Once the bottle cap is removed, CO2 leaves the bottle, and the soda becomes flat. Assuming temperature remains constant at 25 degrees Celsius, and the pressure of the air is 1 atmosphere, how much CO2 would leave a 2-liter bottle if it is allowed to become completely flat? The K value for CO2 is 0.034 moles per liter. Keep in mind that this is not a simple question and will require you to apply knowledge that you have obtained previously in the course, so please take the time to pause the video and try it for yourself. Moving on to the answer for this question, to calculate the amount of CO2 that leaves the bottle, we need 2 things: the concentration in the bottle before and the concentration after. And for that, we need the values for K and the partial pressure before and after the bottle is opened. Well, K is easy. We were given it in the question, and it's a constant, so it will remain at 0.034. The pressure of CO2 in the bottle is also given to us in the question. The only value we don't have is the pressure of carbon dioxide in the atmosphere. Well, as you may have noticed in the previous slide, a table was provided with the partial pressures of many gases in the atmosphere. The partial pressure of CO2 is listed here, and that's perfect, just what we needed. However, be careful. Right now we are measuring in atmospheres, but the pressure of CO2 is given in millimeters of mercury. This isn't too hard to convert, however it is something you're going to want to keep in mind, as Henry's constants are typically given in moles per liter atmosphere. Now we're in business. We have all the values needed to calculate the solubilities before and after, so let's do that. Subbing in 3 atmospheres and the K value, we get 0.102 moles per liter. Subbing in the partial pressure of CO2 in the atmosphere, we get 1.33 times 10 to the negative 5th. We do have to remember that this is asking for the amount of CO2 leaving in a 2-liter bottle, however. And because of this, we multiply both values by 2 to obtain the CO2 contained by 2 liters of soda. Finally, by subtracting these 2 values, we get the overall CO2 leaving the soda to be approximately 0.20397 moles per 2 liters. But what can we tell from this value? Well, we know that the unopened bottle of soda contained roughly 0.204 moles per 2 liters of soda. So just about all of the CO2 contained in the bottle has now left. Because CO2 is what makes soda fizzy, we know that the bottle will be more or less completely flat at this point. Here we have one more quick question, just breezing over some of the theory we have practiced previously. A large body of water is a terrific medium for gases to dissolve into. In the winter, the lake gets colder and the gas content within the lake changes. However, the lake never freezes over. Assuming the partial pressure of all the gases in the atmosphere remain the same, would the amount of gas dissolved in the lake increase or decrease as the winter season approaches, and would the ratio of gases in the lake be altered? Pause the video for a second and try this for yourself. Moving on to the answer, from what we have covered previously, the solubility of gases is negatively affected by increases in temperature. Therefore, the concentration of gases in the lake will increase as the lake gets colder. We also know from Henry's law that solubility is in a linear relationship with partial pressure. If temperature changes, affecting the K value, the pressure will not change and the ratio of gases will remain the same. Therefore, the answer is C. So why would this be useful, and how can we apply these principles to real-life scenarios? Well, there's the examples I gave previously of lakes and soda, but I assume that doesn't interest many people in this course. A much more interesting example for those of you taking biology-related courses is the dissolving of CO2 and O2 in the lungs. Transfer of oxygen and CO2 are conducted through tiny sacs called alveoli. These are connected to your bloodstream, and transfer of gases are driven by the partial pressure of carbon dioxide and oxygen in the atmosphere and blood. Well, that's cool and all, but how would this be useful to us? Gas exchange in the alveoli rely heavily on the partial pressures of O2 and CO2 in the blood and atmosphere. The body pumps low concentrations of O2 and high concentrations of CO2 to the alveoli. The atmosphere contains higher concentrations of O2 and lower concentrations of CO2, facilitating diffusion of CO2 out and O2 into the blood. But what happens when the atmosphere contains lower pressures of both CO2 and O2? This happens in high-altitude tourist landmarks such as Machu Picchu. The lower concentrations of both gases leads to the higher diffusion of CO2 out of the bloodstream and lower diffusion of O2 into the bloodstream. Obviously they aren't around today, but people living in Machu Picchu or other high-altitude places would have developed adaptations to make them retain more CO2 and obtain more O2 from the environment. This is not good news for tourists traveling to these high-altitude places, however, as these people can become very sick if they are left in these places for too long. To summarize what we have learned in this lecture, the partial pressure can be calculated by rearranging the partial pressure formula for the gas in question. Partial pressure is an important part of the Henry's law equation to determine the solubility of the gas. A gas's ability to dissolve in a liquid is lowered with increases in temperature and raised by increases in the partial pressure of a gas. The Henry's law equation states that the solubility of a gas is directly proportional to the pressure of the gas. This law can be applied to most gas solution pairs at a constant temperature. And the Henry's law equation is an important concept for understanding many situations where gas dissolving in liquids is a key factor, such as in carbonated drinks, respiration, and many other scenarios.